Welcome back to ECE 320A. Yeah, you just had an exam apparently, and now you're all excited about. I don't want to scream because it will come through a little bit loud on the mic, but let's get started. Homework number 3 is due tomorrow. Did I get your attention? It's not due tomorrow. It's due a week from Sunday. It's quite delayed, but we'll have some more maybe packing up at the end. Our next exam, I believe, is the 22nd of October, just as a reminder. What I want to do today is recap some of the Laplace transform material, the definition, and just again remind us of a couple of transform pairs. We will then return to our quiz that we had before the exam, dealing with differential equations of a circuit, and maybe we'll look at a second circuit, which might actually be a homework problem. That might also keep you alert. That will then beg the notion that it would be nice to be able to Laplace transform an integral. Let's then derive that relationship. We already know some of the transform pairs relative to a derivative, what that looks like, and we'll see that the integral is really sort of the reciprocal operation of the derivative in the S domain or in the frequency domain. I'm assuming you all remember our two domains, the time domain and the frequency domain, and you need to start getting comfortable working in both of those. We will then derive some Laplace transform pairs. A time domain impulse, what does that have for its Laplace transform? If we now had sinusoids, sine or cosine, what does that look like in the frequency domain? What does a rectangular pulse look like when we transform that? That will then lead us into the notion of working with Laplace transforms or time domain waveforms that are maybe modified from what we have in the table, and how can we make these modified time domain waveforms look like something that we can Laplace transform, or can we apply different Laplace transform theorems to make this conversion possible? And we'll talk about shifting in time. We'll actually talk about sifting today. That was without an H if you couldn't tell. We will look at S translation, or translating the frequency variable S. S, again, is a complex number. That can have a real part and an imaginary part. That's what I want you to be thinking about. And then we will talk about scaling. Here is our recap of where we were before the exam, if you can remember any of that. The definition of the Laplace transform, we have a time domain waveform. We are weighting that with this complex exponential function and integrating over all time. We're now looking at what does this waveform weighted by e to the minus st integrated, what does that look like? We're really collecting all of this time domain information on the function f of t and collapsing it down now into some expression in terms of s. We looked at one particular function, which was the unit step. It turns on at time t equals 0, and it never shuts off. It just keeps going at a value of 1, and we derived that waveform's Laplace transform. If you plug that into the definition of the Laplace transform, you will obtain the frequency domain or Laplace transform of a unit step that starts at 0 is 1 over s. We will, as I said before, start talking about poles and zeros of these different transforms. If you looked at this ratio, 1 over s, I hope it's clear that the denominator vanishes when s is equal to 0. When the denominator vanishes, for those values of s, those are called poles, and we will represent those by x's in the complex s-plane. Here is a frequency domain diagram in the lower right-hand corner of the screen, and that's much different than the time domain waveform. So the left-hand part of our screen is the time domain. The right-hand part is now in the frequency domain, and this is now plotting a complex number that actually represents a pole. So we represent its location with an x, and the value of that x, it's supposed to be right at the origin, is when s is equal to 0. It has 0 real part and it has 0 imaginary part. And that will start to become useful information as we move through this material in this class. Where are your poles? Where are your zeros? What does that mean? What does that do for us? So we need to get comfortable with looking at ratios of polynomials in S and finding when does the numerator vanish. Those will be represented as zeros or circles in the S-plane. Where does the denominator vanish, or for what values of s does the denominator disappear? Those will be our poles, and those are x's. In this case, we do not have any finite zeros, and we have one pole at the origin or at 0. We derived the Laplace transform of a derivative. The derivative is an operation, meaning this s variable can be useful for operating on waveforms and also describing waveforms, and we'll be combining those. But the Laplace transform of a derivative is s times the Laplace transform of the original waveform x of t. And if there's a non-zero initial condition, then we need to incorporate that into the Laplace transform of that derivative. That gives us information about where or how that signal is moving its time rate of change right at time t equals 0. And we subtract that from s, capital X of s. Now, let's get back into business. Here is the circuit that we were talking about before the exam. This now is an RLC circuit, and we want to now find the differential equations that govern the dynamic behavior of this circuit. If you now kick this circuit or excite it, it's going to move in a particular way. By move, I mean its current and voltage are going to respond in certain ways. We want to know, how do we model those dynamics by means of a differential equation? I've already indicated what we talked about last time at the bottom. The number of energy storage elements in this circuit tells us a lot about that particular circuit's behavior. We have an inductor and we have a capacitor, and those two store energy. They're two unique energy storage elements, and because of that, we should expect that this differential equation governing the dynamic behavior in this circuit will be a second-order differential equation. Or maybe it's two coupled first-order differential equations. I've indicated in red the variables that we probably want to, or usually it's nice to focus on or think about writing our equations in terms of the inductor current and the capacitor voltage, which, if you are looking at Eli and ice, those are the last variable in Eli and ice. In an inductor, then, you can say, oh, what's the last variable? That's the I. The current is probably the variable that we might want to try to write these equations in terms of. For the capacitor, it's the voltage. And those are the two quantities that are actually differentiated in the current voltage relationships of the inductor and capacitor. If we now want to write this differential equation, or if you wanted to analyze this circuit, what starts coming to mind as far as how you might come up with an equation that describes the behavior of this circuit? I'm getting even hand signals now. No, not Wildcat, but something else. Is that what I was seeing? Does that make any sense? Am I a square? Don't answer that. But I'm assuming you mean KVL. Is that true? So if this was all resistors, that's begging you to write a KVL equation. Now we can do the same thing with this circuit that now possesses or contains energy storage elements. To break this down into a couple of steps, my current is going clockwise in this circuit, in this mesh. What I want to do now is define these voltages using the passive sign convention, meaning the current's going into the positive terminal before it actually passes through the element itself. And now let me just start by writing KVL in terms of those voltages that I've identified in the circuit. Now I can say, okay, for the analysis, what if I do write the KVL equation, and I'll start in the lower left-hand corner. Now I'm going into the negative terminal of my voltage source. That's now minus V of t. Then I have a voltage drop across the inductor, resistor, and capacitor. And then I get back to where I started. Meaning the algebraic sum of those voltages needs to sum to 0. From a high altitude, this is a valid equation. But this is not a differential equation. This just tells us how the voltages in that circuit are related or connected. We now need to incorporate some of the differential relationships that exist relative to the inductor and the capacitor. And there's where Eli and ice come in. If we now think about Eli and ice, Eli says that the voltage across our inductor is proportional, and the proportionality constant is our inductor. It's proportional to the time rate of change of the current going through that inductor. That's Eli. Ice now has the same structure. It's just we have the current first, which says now that the capacitor current, I sub c, is proportional to the time rate of change of the voltage dropped across that capacitor. And this you should really place into memory. This should just be second nature. V is equal to L di dt, I is equal to C dV dt, where the I and the V are associated with the inductor or capacitor respectively. Let's now use this relationship in the earlier formula that we wrote for our KVL, because now we have expressions that involve the inductor current and the capacitor voltage. We can replace the inductor voltage with L di dt, and we can replace the capacitor, well, let's just leave the capacitor voltage as V sub c for now. So let's now say that we have minus V of t plus L di sub L dt plus V sub r, which is I times I sub L of t plus V sub c of t is equal to 0. Sometimes if I wanted to find a second order differential equation, now I want some forcing term. In this case, that's the voltage source, V of t, in terms of, let's say, the capacitor voltage and its derivatives. Maybe I'm trying to just obtain one higher order differential equation. If that's the case, let me replace the inductor current in terms of the capacitor voltage. Because in this circuit, how is the inductor current related to the capacitor current? It's the same. That allows us now to say that if I want to eliminate I sub L in this equation, I can simply see for this circuit that that's the same as the as the capacitor's current, which is then C dV sub C of t dt. So that everywhere that I have an I sub L, I will replace that with this. And then the only variables in that differential equation will be the forcing voltage V and the capacitor voltage V sub C. Let's do that. We can now say that I have minus V of t plus L times the time rate of change of the inductor current, which is the same as the capacitor current, and that's C dV sub C dt, plus R times the inductor current, which is also the capacitor current, C dV sub C dt, plus V sub C of t is equal to 0. I'm getting tired of doing the d by dt, so I may just use that as V sub C prime or V sub C double prime when it's the double derivative. In this circuit, we are assuming our inductors, capacitors, and resistors are constant. They're not varying with time. They're time invariant. That C can be factored out of the derivative. And now I have one coefficient, which is LC. I have another coefficient, which is RC. And now let me go ahead and do some rewriting of this. I now can say that this is minus V of t plus LC V sub C double prime, that's the second derivative of the capacitor voltage, plus RC times the first derivative of the capacitor voltage, plus V sub C equaling 0. And if I wanted to, you might see this in a more standard form where you normalize the coefficient of the highest powered derivative, or you make it monic. That's all monic means, is you have a 1 on the highest power of your derivative. If we divide every term by LC, we can achieve that goal by just now isolating or making the coefficient of V sub C double prime unity. Doing that, I now have R over L V sub C prime plus 1 over LC V sub C of t, and let me take my source to the other side. I now have ended up with a second order linear time invariant differential equation that governs the dynamic behavior of that circuit. You give me a voltage, V of t, at that signal source, and this now tells me how the voltage of that capacitor varies with time. You just need to solve this second order differential equation. If you know the capacitor voltage, then you can back out the inductor current if you need that by just taking C times the first derivative of that V sub C. Questions on how to analyze that circuit? That means we're primed for another circuit. Let's look at one more. And this one is a little different, and I think you might want to double check this, but this might be problem 31 in chapter 12 of the 10th edition of the textbook. And the circuit looks as follows. We now have a current source That's I sub g of t. I'm probably not going to always include the argument time in some of these. Have an inductor, have a resistor, and we have a capacitor. And we're told that this switch moves at time t equals 0. What's happening before time t equals 0? What is our inductor current, capacitor voltage, resistor current or voltage? They're 0 because that current source is just sourcing a short. And now no current is flowing to the right-hand side of that circuit until time t equals 0. This really establishes 0 initial conditions on that circuit to the right. But once we hit t equals 0, now we engage that current source into the rest of that circuit. And if that's the case, now how do we analyze it? Now at time, or for time t greater than 0, we can effectively erase that second vertical information and just say, now here is our circuit that we are living with or using. And how are we going to try to analyze this circuit? Or what do you expect to end up with as maybe your final answer? Where are you headed, or what do you expect to end up with? And how would you even start answering that? Have a lot of excitement in here. What happened? Before it was really exciting. All I have to do is, to calm you down, is give you a couple of circuit problems, and then it's lights out. Yes. We have some current flowing in all of the elements, won't we? We have some current, and it's going to be divided. If these were all just resistors, you would feel very comfortable analyzing that circuit. Is that true? If the L was a resistor, the C was a resistor, you would say, oh, this is a current divider. So I'm going to have this current I sub G split or somehow shared between those two branches of my circuit. Here you're actually having some differential relationship between all of that because you have energy storage devices. You could now, I hope, if you were given this tonight or tomorrow in some interview, I'm sure that will happen when you walk up and try to give your resume to someone. They'll say, can you solve this circuit, please? That's your entry into this position. Don't go to that booth. They'll ask you for a circuit analysis, right? So for t greater than 0, how many energy storage devices are there? Does that tell you anything? Unless there's some cancellations or combinations going on, generically this would lead to a second order differential equation or two first order. So we're expecting a second order differential equation or two first order differential equations. That's what we're expecting, and you could maybe get a half a point out of a 50-point problem by telling me Eli and Ice. That's not even funny, is it? I do have your exams down below my feet. Oh, are they graded? That might be more of an interesting comment, huh? I just like to carry them around. I threw them down the stairs, and whichever ones got the furthest, they did the best, I think. That's about what was happening this weekend, but I think they've been picked up. So if you see some scuff marks, just take a deep breath. Now, if we now think of these two equations, which variables are we wanting to maybe write the equations in terms of? And I just gave you that typical suggestion a few minutes ago. Usually best to write equations in terms of what? Somebody's currents and somebody's voltages. Do you remember which is which? I told you to focus on those last variables, didn't I, in Eli and Ice? And that now gives you the strategy for how you might try to write these equations. That says that I need to write these equations in terms of inductor currents and capacitor voltages. These are hints. They don't always hold true, but in general, that's a good place to start. If that's the case, we can now start to identify some of these variables in our circuit. I'm just hoping the interviewer will get impatient as I'm just giving more details. Still haven't answered the question, have I? But I've started to write on the circuit. What's one way that you could maybe approach this circuit analysis? How would you now try to find some equations that govern the behavior of that circuit? KCL is a good choice since we did KVL on the last one, and this one doesn't quite look like a one mesh problem, does it? What if we look at KCL at node A? So think about what we have. We have the current coming in from the left, and we have two currents leaving that node. If we now say KCL at node A, we can now say that the current source, I sub G, is equal to the sum of the inductor current and the capacitor current. And actually, if you were reading this problem in the textbook, they've relabeled these. They actually want, I believe, the problem to be solved in terms of the voltage V sub 2 across the capacitor and this voltage V1 across the inductor. And that's not even the variables I said to focus on, but that's okay. We'll try to do what they want. Are those two the same voltage? No, because they have a resistor in between them. But now let's see what we can do. Just writing KCL, can we convert any of those variables into V1s or V2s? What does ICE tell us? ICE gives us a way to eliminate or rewrite I sub C in terms of the capacitor voltage. That's V sub 2. Let's do that. This now says that we can rewrite that as I sub G of T is equal to I sub L of T plus C dV sub 2 dt. We're getting closer. We now have one equation, and at least with a V sub 2 and the source, I sub G. What's our relationship for the current and voltage on an inductor? That's L di dt, and that's Eli, isn't it? So Eli tells us that the inductor voltage, which is V sub 1 of t in this labeled circuit, is now L di sub L dt. And I think the problem is actually asking for a integral differential equation. They're just trying to see if you can pronounce these long words. But that just means that you have integrals and derivatives in this equation that govern the circuit behavior. Can we solve this Eli equation or inductor current for, this voltage current relationship of the inductor in terms of the inductor current? This is why you did your calculus. Now we can integrate both sides and have a formula or an expression for I sub L of t. That's now 1 over L integral from 0 minus to t, because we're throwing that switch at 0. V sub 1, let me use another variable because t is my upper limit of integration. So I'll integrate my variable of integration. Let me just use tau. This I sub L can now go into that location, and now I have I sub G of t is equal to 1 over L integral from 0 minus to t V sub 1 of tau d tau plus C dV sub 2 of t dt. And I won't quite give you the entire answer, but this is now, I think they want two different equations in terms of V1 and V2, and then the second part might ask you to find one ratio that involves V sub 2 of C, or the Laplace transform of V sub 2. What's another relationship that we can write relative to this circuit? We've written KCL at node A. What's another way that we can relate these inductor currents and voltages and capacitor and resistor currents and voltages? We could do a mesh around the right-hand side. If we now looked at this mesh, let me call that mesh B. Let's do a KVL relative to B. Maybe it's not at B, but around B. We have then minus V1 of t plus V sub r of t plus V sub c of t is equal to 0. That's just going around that right-hand mesh. And if we rewrite V sub r in terms of any of these voltages, is that possible? I have minus V of t. What's another way of writing V sub r? That's now Ohm's law, R times I. What's the current through that resistor? I sub c, and we know I sub c is c dv sub c dt. And that's how we will now eliminate v sub r and end up with just v1 and v2. We now have plus r times c dv sub 2 dt, this being simply I sub r, which is I sub c, plus v sub 2 of t is equal to 0. And that's a first order differential equation that relates v1 and v2, and you should be able to use those equations to essentially find the answers that you're wanting in that particular problem. These equations, though, now introduce some new time domain relationships that we might want to be able to put into the frequency domain. We know how to put derivatives into the frequency domain. We don't know yet how to take integrals and put those into the frequency domain. So let's determine what an integral looks like in the frequency domain, or what that transform does in the frequency domain. Let's look at the Laplace transform of an integral. We're now Laplace transforming this integral from 0 minus to t of f of tau d tau. Or, if we plug that into the definition of the Laplace transform, that's now integrating from t equals 0 minus up to infinity of the function itself, which is this integral from 0 minus to t, f of tau d tau. That's the waveform that we're trying to Laplace transform, e to the minus st dt. What we're wanting to do now is make that right-hand side look like something that we've seen before. Yes? So tau is our variable of integration. That's a dummy variable, and in this black box, we are basically saying if we need to know, which we're doing, we're now integrating with respect to time, we have to evaluate that integral. That if we integrate that integral for all time t, that gives us a waveform or another function in that black box as a function of t. That's what we are integrating with respect to in the Laplace transform. So I've simply introduced a dummy variable, tau, or a variable of integration, inside another integration. The outermost integration is the Laplace transform. The innermost is just defining a waveform. That's the integral of some function f. Meaning we're hoping that we have the Laplace transform of f of t. And now somebody says, what's the Laplace transform of the integral of f of t? That's what we're trying to derive. We want to probably get rid of that integral inside the integral. And what part of calculus do we probably need to get this part out of? Integration by parts. Thank you. I couldn't say parts enough, right? This is now going to be a piece of that. Let's say that's our v, and this is now our dw, using our formula, so that now v of t is this integral from 0 minus to t, f of tau d tau. dw is e to the minus st dt. If that's the case, what's the differential of v? What happens when we look at the differential of this integral? We're basically just sort of eliminating the integral so that now we're differentiating the integral or finding the differential of the integral. So that's effectively f at time t. And it's a differential, so that's dt, f of t dt. What's w if dw is this e to the minus st dt? We need to integrate that right-hand side to find w. We have our exponent as something a little bit more than just the variable. It's now a weighted variable of minus s, so we now say 1 over minus s e to the minus st, and that's w. Which, if we apply that in our formula, now we can say we have w, or vw. V was this integral from 0 minus to t, f of tau d tau. W is minus 1 over s, e to the minus st. And we evaluate that at t equal 0 minus and infinity. And then we subtract the integral of w dv. So that now we have w as minus 1 over s, e to the minus st. dv is f of t dt. If I label some of these terms, this was our v, this was our w, so we have vw evaluated at the upper and lower limit. Then we have the integral of w dv. That's the integration by parts. We had the integral of v dw to begin with. That's equal to vw minus the integral of w dv. Let's now evaluate that left-hand piece at both the upper and the lower limit. And what does that provide? We now have minus 1 over s, e to the minus s infinity, integral from 0 minus to infinity, f of tau d tau. So now what I'm doing, I'm looking at the topmost equation, and I had a minus 1 over s e to the minus st. I'm evaluating that at infinity. Yes? Oh, thank you. What are my integral limits? That's still just t equals 0 minus to infinity. So those are my limits in the rightmost integral of that expression. I've now evaluated the first two terms at the upper limit. I need to look at evaluating those at the lower limit. That's minus 1 over s, and it's a minus, so that could be a plus. 1 over s, e to the minus s 0 minus, integral from 0 minus to 0 minus, f of tau d tau. And now I can get these two negative signs on this lower integral. I can say that's now plus. And can I factor out the 1 over s? I'm integrating with respect to t. S is not a function of t. I'm now integrating from 0 minus to infinity. And let me go ahead and just reorder the f of t and e to the minus st so that it starts to look like something I'm used to seeing. Now, we want to evaluate this at values of s where this makes sense, or where these equations converge. S we're going to have be positive. So the minus 1 over s is well behaved in the front. What happens to this term? E to the minus infinity. Since s is positive, that's going to vanish. That's going to annihilate this integral. We're assuming f of t is well behaved, meaning that the integral of f of tau over all time is bounded. And now we are simply scaling that or hitting that with 0. So a bounded times 0 is 0. What's the integral from 0 minus to 0 minus? 0. There's no area underneath a 0 width. And so the top two terms have vanished. What does this look like? I hope that looks like the definition of f of s, so that we've now derived the formula for the integral. And that just says that if you know the Laplace transform of f of t is capital F of s, the Laplace transform of the integral of f of t is just going to be capital F of s divided by s. That's what this whole discussion right now was trying to convince us of. Now, whenever you see this integral of f, let me go ahead and keep with my earlier variable of integration. If we now Laplace transform an integral, that's going to then, in the frequency domain, be the Laplace transform of the original function, f, which is capital F of s divided by s. That's another operation. And how does that compare to the Laplace transform of a derivative? We differentiate. That's equivalent to doing what in the frequency domain? Multiplying by s. We integrate in the time domain. That's equivalent to what in the frequency domain? Dividing. These are reciprocal operations in the frequency domain. We simply have to multiply and divide in the frequency domain and not differentiate and integrate in the time domain. That's why we like the Laplace. Now we just have to do more algebra than calculus. Yes? Where did I get the bounds? I think you're referring to this piece. This is, whoops, what happened? This is this evaluated at the lower limit, t equals 0 minus. The first piece was evaluating at the upper limit, infinity. I subtracted those two terms, v and w, evaluated at t equals 0 minus. Everywhere I had a t in that expression, I replaced it with 0 minus. And I had a t in the upper limit of my integral. And now I'm integrating basically nowhere. I'm stuck. I'm just stuck in one place, and the area under that curve is 0. Does that answer your question? Now, we know a little bit about operations, derivatives, and integrals. Let's go back to waveforms. Let's look at the Laplace transform of an impulse. And everyone knows what an impulse is, right? Oh. Sorry. But you'll never forget. That's maybe better than what I had when I was taking circuits, and I had a rather large faculty member get up on a bar stool and jump off and say, that's potential. We were learning about voltage. And it shook the entire classroom. I can't quite do that. This floor's carpeted. Where were we? Impulse. We know what an impulse is, right? That's this signal that has infinite amplitude. What's the area underneath that impulse? If we integrated that impulse, what would we integrate? Or what would be the result of that integral? What's the area under an impulse? How tall is that impulse? Infinite. How wide is that impulse? What's the support interval in time? Infinitesimal. But the area underneath that is 1. That's the kicker. So and if we were in mechanical engineering, we might have an impulse hammer, and we would hit our mechanical system with a hammer. Don't you wish you could do that in your circuit lab? Oh, this is frustrating. Boom! Hammer it. It's probably not how you see the impulse response in your circuits lab. We're going to derive impulse responses, but we need to understand this impulse. It's just an idealization of a waveform that, what's that going to do? It's not only going to wake you up, but it's waking up your circuit. It instantly energizes all of your energy storage elements. That's what that impulse does. You apply an impulse at, let's say, this voltage source location, and immediately, instantly, all of the energy storage elements have been energized. And then you just watch the circuit respond. And usually it decays, right? That's what I'm doing. That was an exponential decay, if you didn't know. And it had a little shake to it, so it was probably an exponentially damped sinusoid or cosine waveform. Yes? So now if we, and we're getting a little bit ahead of ourselves, but I'm trying to get you thinking about what we're going to be doing. I may ask you on an exam, derive the impulse response of that circuit. That's going to basically be a transfer function description of this circuit's behavior in the frequency domain. And the sort of the thinking or the intuition behind that is, what would happen if I applied an impulse at that particular current source? What that's going to do is that's going to establish some current instantaneously flowing in the inductor, and it will put some kind of charge on that capacitor. And now it's like you somehow initialized that circuit to some conditions, and you want to see how does it respond to those conditions. And that would be the impulse response. And you could watch the capacitor's voltage or the inductor current and say, oh, here's the impulse response due to an impulse at that source and the current flowing through that inductor. And it's basically what's going to happen when you energize those energy storage elements. Let's now move through this Laplace transform of an impulse. I'm going to ask you to recall some fact. If I now integrate from time minus infinity to infinity, the impulse times f of t, what's that going to give me for an answer? Did you see this in calculus? Did you play with any impulses? Maybe not, but let's think through what's happening. Where is this impulse non-zero? For what values of time? It's only going to be turned on at one instant, and that's a very infinitesimally small instant, isn't it? but it's only on at 0. The only way you're going to get anything out of that waveform is if f has some value at time 0. What did we say if that f of t was 1? What's the answer? If f of t was replaced and I said, let me just make that 1, f of t is 1, what's the integral of the impulse? What's the area under the impulse? It's 1, isn't it? For those of you listening, you missed that hint. The area under an impulse is 1. Now what are we doing? Now we are basically taking a snapshot of f of t at time 0, and we're weighting it by 1. What are we going to see at the output? What's the picture going to be? We're taking a picture by that impulse, weighting f of t. What would you expect the output of that integral to be? What's the only value of f that it could possibly be? When's the only time that impulse is active? At 0. All other values, you could now say, oh, I'm going to integrate from minus infinity to t equals 0 minus. That's 0 because the impulse is 0. I'm going to integrate from t equals 0 plus to infinity. Delta is 0, so that's 0. Now I'm integrating from 0 minus to 0 plus. Delta of t, f of t, dt. What's f in that integral? What value of f do you have active at 0 minus to 0 plus? 0. That's the only thing that f is, isn't it? F of 0. And you're weighting that with this impulse that has a weight of 1. You're just extracting that information out of f at time 0. If that's the case, if you believe that, I have some oceanfront property a few miles from here that I'm selling. Yes? So this, oh boy, that's a good question. This is supposed to be the impulse function. That's why I slapped the board or the table to get us thinking that's an impulse. That has nothing to do with the Laplace transform. This is just the impulse function that now is weighting f of t under that integral. If that's the case, what would this integral give us? Suppose I'm still integrating from minus infinity to infinity, but now I have the impulse function of t minus t naught, f of t dt. What's that going to produce? When is that impulse active? When is it non-zero? When its argument is 0. And when is the argument of that impulse 0? When t minus t naught is 0, or when t is equal to t naught. Now we have the impulse active at t naught, integrating f of t over all time. What's the result going to be? If the upper one was when the argument on the impulse was 0, that's the value we used for f. Now what's the result of this integral going to be? It's just going to extract f's value at time t naught when that impulse is active. This now becomes f of t naught. Those are two facts that you need to be comfortable with. You'll use those. If that's the case, now let's look at a particular Laplace transform. And now, here, this L is different from that delta. Is that okay? That's the Laplace transform now of the impulse function. And by definition, that says we integrate from t equals 0 minus to infinity of the function that we want to find its Laplace transform, and that's delta of t. And we scale it by e to the minus st dt. If we now go back to that earlier fact, what's the answer to that integral? So what is our f of t in this guy? E to the minus st. If f of t is e to the minus st, we now want to evaluate f of t at t equals 0. That's our ft, e to the minus st. We said that just needs to be evaluated at times 0. And what's e to the 0? That's simply 1. It can't get any easier than that. If you now Laplace transform an impulse, that gives you a value of 1, and we will call that the sifting property. Do we have any bakers? I'm sorry, not last name bakers, but like a chef or a baker in the audience. Have you heard of sifting? Have you gone down the grocery aisle and you've seen, let's see, I'm looking for some flour, but it needs to be pre-sifted. Well, there it is, pre-sifted. It's always pre-sifted. In the old days, it wasn't, and we had a sifter. So now when I do this, I'm sifting flour. And you needed to do that for your pie crust to be nice, so that we could have a pie. This is the fall semester, so we don't have pie day, do we? So we can't sift. Well, we can sift because we can do it mathematically. This is sifting. What's it sifting? It's sifting that function's value at times 0. And that's what we were doing with the flour. We were basically not allowing the big chunks to come out. We had a nice pre-sifted flour, or we were able to sift our flour. Whew. All right, let's move on. We want to now start Laplace transforming sinusoids. But we're going to do that indirectly. We're going to do it by realizing that we can represent sinusoids as a combination of complex exponentials. Meaning, let's just see if we can Laplace transform this generic exponent, e to the gamma t, and we'll let gamma be different things. But right now, let's just make it a variable gamma. What's the definition of the Laplace transform? We integrate over time from 0 minus to infinity. The waveform that we're trying to Laplace transform, in this case, that's e to the gamma t. We weight that by this complex exponential, e to the minus st, and integrate with respect to time. But we know all of these facts or techniques of combining exponents. We can now, we're multiplying terms that have exponents, we can add the exponents. They're all raising e to this, we're using the same base. So that we now have e to the minus, let's say now this is s minus gamma t dt. Again, this is why you studied your calculus. What's this integral? If it was the integral of e to the u du, what would that be? It would be e to the u, wouldn't it? But now we don't have just u, we have some combination of variables. We now have 1 over minus s minus, whoops, that's a gamma, not an alpha, gamma e to the minus s minus gamma t, evaluated at 0 minus and infinity. This now, let me pull out the minus sign. I have, well, what happens at the upper limit? It's 0, isn't it? So now let me just evaluate. So it's 0 minus the lower limit. Really? And what's e to the 0? That's 1. And we have a minus. This actually ends up being 1 over s minus gamma. That's the Laplace transform of e to the gamma t. It's 1 over s minus gamma. Now we can evaluate that for all sorts of choices of gamma. That was the beauty of doing this once. Suppose I now look at gamma. That's e to the gamma t, and what's the Laplace transform of e to the gamma t? Creating a table. Suppose that I want gamma to be minus sigma, where sigma is positive, so that now I have a negative exponent. I have an e to the minus 6t, for example, or an e to the minus 10t. I know that this is e to the minus sigma t. And based on what I just derived, I replace gamma with minus sigma in this 1 over s minus gamma formula, and the Laplace transform of a decaying exponential is 1 over the quantity s plus sigma. If we sketched the s-plane, do I have any zeros in that ratio? Do I have any values of s that cause the numerator to vanish? Are there any s's in the numerator? No. So there are no zeros. Do I have any values of s that cause the denominator to vanish? What value of s will cause that to vanish? Negative sigma. So that would give me a pole at minus sigma. And that pole is in the left half plane. That will become important information. What if I allowed gamma to be a complex number, j omega, a purely imaginary number? Now I raise e to j omega t, and based on my derivation of the Laplace transform, I now have 1 over s minus j omega. Do I have any zeros in that ratio of polynomials? Is the numerator, does it even have any terms in s? No, it's a constant. There's no s in the numerator, so there's no s that will allow the numerator to vanish or to be equal to 0. What value of s causes the denominator to vanish? J omega, that's a pole. And now I go into the imaginary axis, a distance omega. That's j omega. J is up and down. What about I look at minus j omega for gamma? This is now e to the minus j omega t. That's now 1 over s plus j omega. And in terms of my poles and zeros, I now have a pole at minus j omega. One more. What if I allow gamma to indeed be a positive value, a positive real number? This is now e to the sigma t, e to the 6t, e to the 20t, e to the 2t. What's that doing as a function of time? It's going exponentially unbounded, isn't it? E to the 2t, e to the 5t. That now has a Laplace transform of 1 over s minus sigma. The value of s where that vanishes is over here at sigma. This chart is now instrumental in us trying to figure out the Laplace transform of many different waveforms. We now know the Laplace transform of an exponentially decaying waveform, e to the minus 2t. That's 1 over s plus 2. We have e to the j omega t and e to the minus j omega t, but Euler is going to come to the rescue now, or we now can rewrite cosine. We can now say that the Laplace transform of the cosine omega t, I can rewrite that as a combination of complex exponentials. Cosine omega t is e to the j omega t minus plus e to the minus j omega t over 2. You remember that? That's the cosine. So the cosine, if you remember Euler told us that we had e to the jx was cosine x plus j sine x. Well, if you play with that, you'll see that you can make cosine of omega t equal this combination of complex exponentials. But if this is the cosine, do you see that now if I look at rows 2 and 3, I can come up with the Laplace transform of the cosine? The Laplace transform of the cosine, let me say that this is sort of a note aside. This is now equal to 1/2 the Laplace transform of e to the j omega t plus 1/2 the Laplace transform of e to the minus j omega t. I'm just using some linearity properties of that expression. I'm factoring out the 2 in the denominator, and I'm left with the numerator, and I've just separated that into the 2 parts. Row 2 tells us what the Laplace transform of e to the j omega t is, and row 3 tells us the Laplace transform of e to the minus j omega t. If I plug those in, I now have 1/2 over s minus j omega plus 1/2 over s plus j omega. And now I get to do some algebra. I have s minus j omega, s plus j omega, 1/2 s plus j omega plus 1/2 s minus j omega. What do I have in the numerator? I have j omega over t minus j omega over t. Those cancel, and I have 1/2 s plus 1/2 s. I end up with s. What's in the denominator? That's now the Laplace transform of my cosine. S over s squared plus omega squared. And